Okay, so this is November the 13th. This is Math 1314. I have a couple of announcements for everybody to get started here. First of all, WebAssign. I've done a little bit of reconfiguring of the WebAssign homework here at the end. I've eliminated a few assignments. I've kind of split one assignment into two assignments. So it's not going to affect anybody because nobody has, not going to affect anybody directly because no one has actually started those assignments yet. So that's fine. The next due date is November 21st. So that's a week from tomorrow. That's the day before Thanksgiving break. So pay attention to that. The next couple of assignments are due on that day. And then after that, there will be a couple of assignments due on December the 6th. And those will be the last assignments due. And I'm probably going to give you one paper and pencil assignment at the very end on the very last topic that we're going to cover. I'll send that out as an email. It will be something that will not necessarily be due for a grade. I may give some extra credit possibly for people who complete that and turn it into me. You'll just be looking for that over the next probably 2 weeks, something like that. All right, so a little bit about the schedule and the way things are going to finish up here because we're really rapidly finishing up the semester. So schedule for the rest of the semester. So this week, that would be November the 13th, which is today, we're going to cover solving exponential equations. Last time we did properties of logarithms, so today we're ready to deal with this topic. So we're going to look at exponential equations. On the 15th, we're going to look at log equations and solving log equations. And that'll finish up our discussion of exponential and logarithm functions. Next week, and Exam 3 review posted by the end of the week. I've started working on your Exam 3 review, and that should be posted by the end of this week. Next week, so that's November the 20th, that'll be a week from today. We're going to turn our attention to systems of equations and solving systems, particular type of systems, but I'm just going to say solving systems right now. 11/22, which is next Wednesday, there will be no lecture because that is the beginning of the Thanksgiving weekend. And so no lecture on the 22nd. And then the following week, so that's the week after Thanksgiving, on the 27th, we're going to essentially start our last topic, and we're going to be talking about solving systems again, and an introductory topic on matrices and using matrices to solve systems. 11/29, no lecture, as I'll be on campus that day. And then on 11/30, the Exam 3 window opens. All right, and then the following week, we'll talk about that, but there's one last week at the end of the semester, and we'll do a little bit of work there. We'll finish up anything we have to do with matrices. So there'll be one last week at the end of the semester, and probably one last lecture on November the 6th. This will be our last lecture right here. So we are rapidly finishing up the semester. Really not much left to do for the semester here. And we're starting to talk about finishing up certain things. So exam 3 is going to come up. We'll have an exam review. There is a review for the final exam that I'll be posting probably sometime hopefully by Thanksgiving, somewhere around there, so that you'll have a detailed look at what's going to be on the final exam. And so you have lots of information coming up here at the end. Also remember, let me flip the screen here, that the W day, the last day to drop the class, last day to drop and receive a W is today. All right, so if you're watching this lecture later on today, you still have today to drop the class if that is what you were choosing to do. As I always recommend to all of my students, I would recommend you talk to me before you do anything to see what the status of your grade is. So I had an email this morning from a student in another class about their status in the class. So please don't hesitate to contact me if you have questions. All right, so today we are going to be talking about solving exponential equations. Last time we started talking about and looked at properties of logarithms. We're going to use properties of logarithms during the day today. So we'll be going back over those again. So we're talking about solving exponential equations. And if you remember, an exponential equation is what started all this stuff about logarithms. Probably 3 lectures ago, we were confronted with this problem. We were confronted with a compound interest problem that went something like this. First of all, that's our compound interest formula, A equals P times 1 plus R over N to the NT power. And we were investing something like $1,000. So that was our principal, was $1,000. The interest rate, we'll say, was 4%. And so remember, that means you have to write R as 0.04. Interest was compounded quarterly. So since it's compounded quarterly, that means it's compounded 4 times a year, and so that means N is 4. But the question went like this: how long before the account grew to $2,000? In other words, how long before it doubled? That would be another way you might see it worded. How long before the account doubled in value? Now, if you think about it, the question here now, how long, means that time is the unknown. And so when we substitute this information into our equation, A is going to be 2,000, our principal, because that's the amount we want to have at the end. The principal, the amount we invested at the beginning, was 1,000, and then we had then times 1 plus 0.04 divided by n, which was 4, raised to the nt power. N is 4, but t is our unknown. And this is the issue in this problem, is that the variable that we're solving for is in the exponent. And so we end up with what we call an exponential equation. Now, first of all, you could do the arithmetic. 0.04 divided by 4 is 0.01. And so then 1 plus 0.01 would be 1.01 to the 4t, like this. And then you could divide both sides by 1,000 here, and you get 2 equals 1.01 raised to the 4t power. And this is an example of what we call an exponential equation. And up to this point, we were kind of out of luck as far as solving this kind of equation, but now using logarithms, we can solve this type of equation. That's what we want to talk about today. So we're going to be talking about this kind of equation in a few minutes. All right, and so exponential equations is our topic for the day, solving those. And there's actually two types of exponential equations we want to look at. One where the method is a little bit easier, and then one where we have to use logarithms. So on this problem, on this equation, we must use properties of logs to solve this equation. We must use properties of logs to solve. Now, first, what we want to do is look at equations where we don't have to use properties of logarithms to solve them. And there are some like that. So there are two types of exponential equations that we're going to look at. The type 1 equations, the ones we're about to look at, you don't need logarithms for these. So do not need logs. And these are equations where you can use this property of exponents instead. You can use the property that if you have b raised to the x power equals b raised to the y power. Notice that in that equation, the bases are the same. And if you get that the bases are the same, because of the way the graph of the exponential function looks, in other words, that it's a one-to-one graph, because it's one-to-one, it's got to be true that those exponents have to be equal also. So if you've got an exponential expression equals an exponential expression, and the bases are equal to each other, the only way it could be true is that the exponents are equal to each other also. So for example, we have this equation, 3 to the 2x plus 1 equals 3 to the 4th power. Notice that the bases are equal here. Right. And if the bases are equal, the only way that this could be true, is if 2x plus 1 was the same thing as 4. It could not, there's no other way that that could be a true statement unless those exponents had to be the same. And so we can then notice, then you don't have the x in the exponent anymore, right, when you write that second equation. And so we can now solve this equation and we get the solution very quickly. Get 3/2 is the solution to that equation. And you can certainly check that with no problem. You have 3 to the 2 times x power. X is 3/2. And we want to see if this is equal to 3 to the 4th power. And what happens here, the 2's divide out. You get 3 plus 1. And certainly you get 3 to the 4th equals 3 to the 4th. It checks. Right, so 3/2 is our solution. So this is the property for a type 1 exponential equation that we will use. It's a property of exponents. It just says if the bases are equal, then the exponents have to be equal also. All right, so here's our first example right here. Now, it may not always be quite that direct, first of all, but let's look at another equation before we do anything a little bit more complicated. So let's say we have 5 to the 3x minus 4 equals 5 to the x plus 8 power. Right? So once again, in this problem, the bases are equal. And because the bases are equal, once again, the only way that could be true is if the exponents are equal also. So it has to be true that 3x minus 4 and x plus 8 are equal to each other. And then you end up with a simple equation, in this case a linear equation. You could subtract x from both sides. You get 2x minus 4 equals 8. You could add 4, you get 2x equals 12. Divide by 2, you get x equals 6. You could certainly check that. If you wanted to look at the check, you get 5 to the 3x minus 4 power equals 5 to the x plus 8 power. And so notice you get 18 minus 4, or 14 here, and you get 14 here. You get 5 to the 14th on both sides. The two sides are equal to each other, it definitely checks. So x equals 6 is our solution to this equation. All right, so this seems to be a pretty straightforward type of problem. Now, it's generally pretty straightforward, but there can be complications to this kind of problem. So let's look at those complications a little bit. And I know there's always, it seems like there's complications, isn't there, in algebra. But let's say we have 2 to the 3x minus 4 equals, let's say, 32. Now, at first, this looks like it's not a type 1 kind of equation because the bases are not equal to each other. But that's true. The bases are not equal. No question about that. But the bases are both powers of 2. Bases are both powers of 2. And so even though this is not directly a type 1 equation, it can be made to look like a type 1 equation. And the reason is that 32 is really 2 to the 5th power, right? And so if you just write 32 as 2 to the 5th, now you get that the bases are the same. And so now bases are equal. And so now you can solve that equation just like we were doing on the last screen. You know that the bases are equal, so the exponents have to be equal also. You add 4, you get 3x equals 9. Divide by 3, you get x equals 3. You can check that. I think it's a good idea to check these kinds of problems just because it's easy to make a common careless mistake in these exponent kind of problems. Okay, so our question, if we substitute 3 in place of x, sure enough, what do we get here? We get 2 to the 5th power equals 32, which is true. All right, so that seemed to be okay. So now let's look at another example and start looking at things that may be a little bit more complicated. So now we have 9 to the 2x minus 5 equals 27. All right, so definitely no question that these bases are not equal. Bases are not equal. However, once again, bases in this case are both powers of, and let's see, we have 9 and 27 are both powers of 3, right? We know that 3 to the 2nd power is equal to 9, and 3 to the 3rd power is 27. And so we take advantage of that in this problem. These are both powers of 3, and so we write them that way. Now you have to be really careful. This is 9 to the 2x minus 5, so we are replacing the 9 with a 3 squared, and so this would be 3 squared to the 2x minus 5. And then 27 we'd rewrite as 3 to the 3rd. Right, so we write everything as powers of 3. Now remember what the rule of exponents is. When you have something raised to a power and then raised to a power again, you multiply the exponents. And that's what I've got right there. I've got 3 to the 2nd to the 2x minus 5. So you've got to multiply those exponents together. And because you're multiplying them like that, you have to use distributive property there to multiply that out. So you have 3 to the 4x minus 10 equals 3 to the 3rd. And now the bases are equal. Right? Now the bases are equal. And so now I can equate the exponents. Right now the exponents have to be equal also. And then you can go on and solve the equation, right? Add 10 to both sides, divide by 4. All right, so, and then we get 13/4 is the solution to this equation. Again, you could certainly check to make sure that this worked. Never a bad idea to check this. So you have 9 to the 2 times 13x minus 4 minus 5, like that, right? 2x minus 5 is supposed to equal 27. The check on this is going to be a little bit more difficult. The 2 and the 4 cancel, so that gives you 9 to the 13 halves minus 5 equals 27, because the 2 and the 4 divided out. And then that's 13 halves. I'm going to go ahead and do this off to the side. 13 halves minus 5 in the exponent is 13 halves minus 10 halves. Got to get a common denominator there. And that would give you 3 halves. So this ends up being 9 to the 3 halves equals 27. And it's been a few days since we've talked about this, but remember that this is the power and this is the root when you've got a fractional exponent like that. And so this really means the square root of 9 raised to the 3rd power. And sure enough, what is the square root of 9? It's 3. 3 to the 3rd power is 27. And so you do get 27 equals 27. It does check. A little bit more involved there, and you had to use some things that you knew about exponents that we've talked about a couple weeks ago to finish that problem up. All right, so this one was a little bit more complicated. Still involved getting the bases to be equal, right? Every one of these problems, we're looking at getting the bases to be equal on each side of the equation. And if we can get the equation to look like that, then we can equate the exponents. All right. Last problem we're going to look at for a type 1 kind of problem, definitely a little bit more complicated. Let's say we have 8 to the negative 3x times 1 over 4 raised to the x plus 3 power equals 16 to the 2x power. Now this definitely looks complicated. It's definitely an exponential equation. It's got x's in the exponents, but it looks like a mess. But notice that all the bases here, all the bases, and the bases in this problem are 8 and 4 and 16, all the bases are powers of 2. And because they're all powers of the same number, we can use the property that we've been discussing to solve this problem. It's just going to take us a little bit to do this. Just take it slowly, take it one step at a time when you do this. So take the 8, the 4, and the 16, and write them all as powers of 2. The 2 squared is 4, 2 to the 3rd power is 8, and 2 to the 4th power is 16. Right? And so go through and write all of those bases as powers of 2. So the 8 is 2 to the 3rd power, and that's to the negative 3x. And then times, and this is 1 over 4, which is 2 squared, to the x plus 3, equals, and then 16 would be 2 to the 4th power to the 2x. All right, so I've written everything as a power of 2, and now you've got to start dealing with rules of exponents. So the 2 to the 3rd to the negative 3x would be 2 to the negative 9x. Remember, you multiply exponents there. All right, so 3 times negative 3x is negative 9x. Now you have to be careful with this fraction, that the 1 over 2 squared, rewrite that as 2 to the negative 2 to the x plus 3. If you've got a base in the denominator, you need to bring it to the numerator and then change the exponent to a negative. And then on the right side of the equation, this would be 2 to the 8x power, because you multiply the exponents over there. Right, so this is just 4 times 2x. You just multiply the exponents, and that gives you the 8x right there. Just like on this side, you had 3 times negative 3x gave you the negative 9x. Still have a little bit of work to do here, because remember, you need a base to a power equals the same base to a power, and I don't have that yet. So you have 2 to the negative 9x times, and then you multiply these exponents. So this would be 2, and you have to use the distributive property there. That's negative 2 times x plus 3 is negative 2x minus 6. So this is 2 to the negative 2x minus 6 power equals 2 to the 8x power. Okay, now, and this is multiplication all the way through there, now you've got bases being multiplied that are like bases. And remember what that rule is. When you had x to the a times x to the b, that's x to the a plus b, right? You add the exponents. So this should be 2 to the negative 9x plus negative 2x minus 6 power equals 2 to the 8x. And that would give me 2 to the negative 11x minus 6 power equals 2 to the 8x. Wow. Right, and finally, what do? We get bases are equal right here. I mean, it took us a lot to deal with that and get it to that point. That's our goal. And you know you can get to that if you've got a bunch of multiplications in the problem and all of the bases are numbers that are powers of the same number. So in this case, 8, 4, and 16 were all powers of 2. So we knew we could get to this point eventually with rules of exponents. So now we just equate the exponents when we get to this point. So negative 11x minus 6 has got to be equal to 8x. You add, let's see, I'll add 11x to both sides. So that gives me 19x over here. And then divide by 19, and you get negative 6/19 is equal to x. And now I'll leave the check for you on this one. The check is certainly more complicated, definitely more complicated in this problem. But negative 6/19 is the solution here. And if you check it, you'll find that it does make it a true statement. All right, now if you flip back, all of these problems were type 1 equations. All of them were ones where the bases were the same. Every problem we've looked at, the bases were all the same through all 4 of these that we've looked at. And now let's look at the type 2 equations. The type 2 equations are ones like the problem we started with here. If you look at the bases there, like here I've got 2 equals 1.01 to the 4t, there's no way that I can get the bases to be equal to each other. And so we have 2 equals 1.01 to the 4t. This is an example of a type 2 exponential equation. The bases cannot be written so that they're the same number here. Right? The bases are not equal and are not powers of the same number. Bases are not equal and cannot be made to be equal. And so this is a type of problem where we must use properties of logarithms. So use properties of logs to solve this equation. And so this is how we do this. And we take advantage of this property that if 2 numbers are equal, capital A is equal to capital B, then if you take the log of both sides of these equations, or both sides of this equation, their logarithms have to be equal also. No matter what the base in the logarithm is, those bases or those logarithms have to be equal to each other. There's no question about that. And again, it's because the logarithm function is a one-to-one function. Because it's a one-to-one function, this has to be true. So 2 is equal to 1.01 to the 4t. So it must be true that the logarithm of 2 is equal to the logarithm of 1.01 to the 4t. So what I'm doing here is I take the log of both sides of the equation. Take log of both sides. Now notice the logarithm I'm using here is a base 10 logarithm because I use just log without writing a base down. I could use any base I wanted to because we're going to be looking for decimal approximations at the ends of these problems. I'm either going to use a base 10 logarithm or a base E logarithm and use the natural log on both sides of the equation. And sometimes there's other considerations also, but those are the 2 logarithms that we're going to generally use when we're taking the log of both sides of the equation. Now, why does this help us to solve this equation? Well, the problem was, the reason why we couldn't solve this equation at the beginning is because the t was in the exponent of this exponential equation. And, we got to get that t out of there somehow. And so to get the t out of the exponent, what we do is we use the power rule for logarithms. Use the power rule for logarithms. And see that 4t is in the exponent, but I have a power rule that says I can rewrite that 4t in front as a factor. And I've got that equation right there, right? I just bring that 4t down in front as a factor, and now I've got the t out of the exponent, and now I can solve this equation for t. Now I want you to notice that there's two factors over there with t. There's a 4 and a log of 1.01. The log of 1.01 is a constant, and so just like of the 4 is. And so what I'm going to do is I'm going to divide this side of the equation by 4 log of 1.01. And so that will mean that the 4's will divide out, and the log of 1.01's will divide out. And I will be left with a t on that side of the equation. But what do you have to do? You have to divide the other side of the equation by 4 log of 1.01 also. And so there's the solution right there. Now, a couple of things. One thing is WebAssign frequently, unless they specifically ask you, are going to ask you to write the answer, the exact answer. And so this is the exact solution right here. And they're going to ask for this, and they're going to want you to write it out like this. As log of 2 over 4 log of 1.01. Now, you have to be careful if you're going to enter this correctly, whether it's on WebAssign or on a calculator, on a graphing calculator, you have to put parentheses around probably the 2 in the numerator, so it'd be log of 2 in parentheses, and then the fraction bar. And because there's an operation going on in the denominator, you really need to put that in parentheses also, because you want the calculator or WebAssign to do the 4 log of 1.01 first. And by the way, because of the way a graphing calculator operates, you're going to have that 1.01 in parentheses also. So that will close off the parenthesis and the 1.01, and then you'll need a second right parenthesis to close off the multiplication that's in the denominator like that. And so you have to enter it like that. And so in WebAssign, this is going to be your solution, probably, and most of the problems on the WebAssign homework. You're going to want to enter it as log of 2 over 4 log of 1.01. But remember what this was. This was an application problem, and you were asked how long it took the money in this account we were looking at to double. And you wouldn't tell somebody, well, it takes log of 2 divided by 4 log of 1.01 years. That wouldn't make any sense to do that. It'd be goofy. If you went into a bank and they told you that, you might want to walk out of the bank, right? Because you don't know what they're talking about, even though they might be right? But what we're going to do, we're going to enter this on our calculator, and you definitely want to enter it like I just did right here on your calculator. And so I have log of 2 divided by, and then I'm putting that denominator in parentheses, and then I have 4 log of 1.01. I close the parentheses off at the end there, and I get about 17.4 years. So you get t is equal to about 17.4, and that is the answer to the question, is that it would take about 17 to 18 years for the money to double in that account. So it takes quite a while for it to double like that. All right, so this is the kind of problem that we want to look at now. This is an example of a type II exponential equation, and so we want to look at a couple of more type II exponential equations and using properties of logarithms to solve those. All right, so let's look at another couple of problems here. So the next example, let's say that we have 3 to the 5x minus 2 equals 30 power. So notice this is a good example of a problem where the bases are not equal, and 3 and 30 are not powers of the same number. Right? 3 and 30 are not powers of the same number. And so this is an example of a type II exponential equation, right? And where the bases are not the same and they can't be made to be the same. So what do we do to solve this type of equation? We use properties of logarithms, right, to solve for x. So what we're going to do here is we're going to take the log of both sides of the equation, and just to be different from the last problem, I'm going to take the ln of both sides of the equation. I'm going to take, remember, that's logarithm base e. That's the natural logarithm. It doesn't matter which logarithm base we use, and web assignment shouldn't matter either. So using natural log would be just fine. And as far as the decimal at the end, not going to be a problem. So I use the power rule here for logarithms. This is why you're using logarithms here, because we have this power rule. And that power rule allows us to take the exponent and bring it down as a factor. So you have 5x minus 2 times log 3, natural log of 3, equals natural log of 30. All right, and so now we're going to solve for x. Now to solve for x, think about, you have the natural log of 3 sitting there, but, if you had an equation like this, 5x minus 2 times 6 equals 17, let's say, right? What would you do first probably to solve that equation? You'd probably multiply through by 6, get 30x minus 12 equals 17, and then solve the equation. Well, that's what we're going to do here. We're going to multiply through by natural log of 3. Now, this looks funny to a lot of people because we're multiplying through by a logarithm, but that natural log of 3 is just a constant. So you use the distributive property the same as you always would in this kind of problem, this kind of multiplication problem. So you have 5x natural log of 3 minus 2 natural log of 3 equals natural log of 30. All right, stick with this. You'll be able to solve this. You just have to be careful. So now, go back to this problem over here on the side, that 30x minus 12 equals 17. What would be the next thing you do? The next thing to solve this equation is you'd add 12 to both sides, right? You get 30x equals 29. Well, that's exactly what we're going to do here. We have this constant, 2 natural log of 3, and so we'd add that to both sides of the equation, just like the 12 over on the side, on that side problem there. So that'd give you 5x natural log 3 equals 2 natural log 3 plus natural log of 30. All right, and then you could divide both sides of this equation by 5 natural log 3. Like that. And so the 5 is divided out, the natural log of 3 is divided out, and you're left with x. And you have this messy looking expression over here, 2 natural log 3 plus natural log 30 divided by 5 natural log 3, like that. And in WebAssign is going to ask you to use that solution and to enter that in the box on WebAssign, right? Now, when you do that, you're going to have to use parentheses here, probably liberally. You're going to be using them a lot here because you have the parentheses around the numbers you're taking the natural logs of, but then you have to put parentheses around the entire numerator also, and then divide by, and then parentheses again, and then 5 natural log parentheses 3. So, on a graphing calculator, you're going to have to be really careful about how you enter that, and you're going to have to put parentheses in the correct spots in there in order to enter this correctly. And I'm going to ask you on an exam, I'm going to ask you for the decimal approximation for these kinds of problems. So I just want you to kind of be aware of that. And I'm going to show you a different way to get an answer here also, a different form that on a calculator might not be so bad to use. Let me go ahead and enter this on my calculator. So I'm 2 times natural log of 3 plus the natural log of 30. Close the parentheses off there, and then I put it divided by, and then another set of parentheses, and then 5 natural log of 3. Close the parentheses, close the parentheses. Not a bad idea to do what I just did, in that I wrote it out with all the parentheses in the correct places. I actually wrote it physically on my screen, in your case on your paper. Write it out like that with all the parentheses in the right spot, and then translate it over to your calculator. I think that would make it much easier to be able to get the correct solution here. So I get 1.0192, and I'll typically ask for 3 or 4 decimal places, and so this is rounded here to 4 decimal places. I will specify in the exam how I want you to round it. I'm not going to make a big deal about rounding, to be honest with you. I'm not trying to go out of my way to penalize you for rounding it. I want you to get to the right answer. I want you to have the calculations done correctly. Now, another way you could have done this problem for a calculator is when we got to this spot right here. You take the log of both sides the same, but instead of when you have 5x minus 2 times natural log of 3 equals natural log of 30, instead of multiplying through using the distributive property there, what you could do is divide both sides by ln3 right away. And when you do that, you get 5x minus 2 equals natural log of 30 over natural log of 3. And then to solve for x, you add 2 to both sides. And then you divide that whole thing by 5. Now, when you divide both sides by 5, it looks ugly to write it that way. You have natural log of 30 over natural log of 3 plus 2 all over 5. But that is a correct way to write the expression. Now, you're going to have to check on WebAssign whether WebAssign would take that answer. But that is not a bad answer to enter on your calculator. And I think some students find it a little bit easier to get to this form rather than using the distributive property and then using their calculator on that form right there. So if you did that on your calculator, and I'm going to write that on the next page, I'm going to go ahead and paste it onto the next page right here. So on your calculator, if you're going to enter this form, this would be the natural log of 30, put the 30 in parentheses, divided by the natural log of 3, put the 3 in parentheses, and then that would be plus 2, like that, and then that whole thing goes in parentheses, and then divided by, and then 5. No parentheses needed in the denominator there. So if I enter that on my calculator instead, I better come up with the same thing, right? So and again, notice I wrote it out first so I could see it in front of me, and then I have an easier time entering it on my calculator with all these parentheses running around in there, and I make sure I get everything right. I think that's a real advantage to do that. And you do get 1.0, right? The same answer. You get 1.01918, blah, 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 like that. And so that is the same answer. You definitely need to check WebAssign to see whether WebAssign will take it like that. And frankly, I don't know whether they do or not. So that's something that you'll have to check to see if WebAssign will accept the answer like that. I think it may be the case that they will. So, but you'll have to check that. All right, next problem I want to look at. So we're talking about these type II exponential equations. So you have 10 to the 7x minus 1 equals 15 power. Let's say it's 10 to the 7x minus 1 equals 15. Now in this case, notice that the base on the exponential expression is 10. So since the base is 10, use log base 10. Use the common logarithm for sure here, because that's going to make your calculations easier at the end, and I'll show you why. So don't use natural log here. I mean, you can. It's not wrong to do that, but you're making your life harder by doing that. So I'm going to take log base 10 on both sides of the equation right here. And when we use the power rule, remember that's why you're doing this. Right, so I bring that 7x minus 1 down in front as a factor. And then I have 7x minus 1 times log of 10 equals log of 15. And this is why this makes sense to do what I just did and use log base 10 here, is because what's log of 10 equal to? Remember that this is really logarithm base 10 of 10, because it's a common logarithm, and that's the power you raise 10 to get 10, that's 1. See, so this factor right here goes to 1. It's equal to 1, and so that makes my life so much easier here, because that factor just goes away, because it's just 7x minus 1 times 1. Right, and so it goes away, it's gone. And so I've got 7x minus 1 equals log of 15. And so now you can solve for x by easily just adding 1 to both sides. By the way, I would not write this as log of 15 plus 1 like that. I mean, it's not wrong to do that, but then it starts getting confusing as to what you're taking the log of. And so I would always put the 1 in front. That way it's very clear. So you have 1 plus log of 15. And then divide by 7. So you have x is 1 plus log 15, all divided by 7, like that. On WebAssign, that's the way they're going to want you to enter it. On a calculator, right, what are you going to have to do? You're going to have to enter the 1 plus log 15, like that. And then that entire numerator has to be put in parentheses because of that addition, and then divided by 7, like that. And so on the exam, I am definitely going to ask for that answer, for the decimal answer here. So be prepared for that I'm going to ask you to do that. So when you do this calculation here, I get 0.31087 approximately. So x is 0.3109 power. And this is rounded to 4 decimal places. And so that's our solution right here. Remember, you can always check this. You would need your calculator to check it, but you could certainly check this problem and see that this is actually valid. What you're doing is you're using approximations to do that, but you could do that. So you'd have 10 to the 7 times 0.3109 power minus 1 equals 15. And so what I might do in my calculator is some intermediate steps. I might take 7 times 0.3109, and I get 2.1763. So I have 10 to the 2.1763 minus 1 power is supposed to equal 15, like this. And then I subtract 1, and so that would give me 1.1763. So 10 to the 1.1763 equals 15. And then I actually do that arithmetic. I use 10 and then use the caret symbol. And I divide that out, or do the arithmetic rather. And I get 15.007. And that certainly is approximately 15. Now you remember, you're not going to get exactly 15 on the left side of the equation because I did round this decimal at the beginning of the problem. The 0.3109 at the beginning, I rounded that up. And so it makes sense that my answer is going to be a little bit too big here. But it's close enough that it would tell me that I'm quite likely right here in this problem. All right. So continuing to discuss some things about type 2 exponential equations. So the next one, let's say we have 25 times e to the 3x minus 5 power minus 50 equals 100. All right, so this looks a little bit more complicated. This is not going to be too bad. Now you do have an exponential expression sitting in there. This e to the 3x minus 5 is my exponential expression. All right, that's the exponential expression. And so you want to get that thing by itself if you're going to try to solve this equation, right? You want the exponential expression isolated and a constant on the other side of the equation. So what you're going to do here is you're going to add 50 to both sides of the equation. And so you get 25 times e to the 3x minus 5 equals 150. And then go ahead and divide both sides by 25. And you have e to the 3x minus 5 equals 150 divided by 25. And 150 divided by 25 is 6. So you have e to the 3x minus 5 equals 6. So you want that exponential expression by itself before you use properties of logarithms. And on this problem, the base is e on the exponential equation, on the exponential expression. And since the base is e, use natural log on both sides of the equation. So use ln on both sides. Again, you could use base 10 if you wanted to, but it doesn't make any sense to do that. This is going to make your life easier by using natural log on both sides of the equation. So I use natural log of e to the 3x minus 5 equals natural log of 6. Now remember, natural log is just an abbreviation for logarithm base e. So that's going to be to your advantage to do that in this problem. So now you use the power rule on logarithms, and you bring the 3x minus 5 down in front. And you have 3x minus 5 times natural log of e is equal to natural log of 6. And then natural log of e, what's that equal to? Don't forget, if you get confused on the natural log, you can always write it as logarithm base e. And remember that this represents the power you would raise e to get e. This is 1. Natural log of e is 1. And so this factor goes away, just like it did on the last problem when we had base of 10. So you end up with 3x minus 5 is equal to natural log of 6. And now it's a relatively straightforward problem to solve. Right, go ahead and add 5. So you have 5 plus natural log of 6 on the right side of the equation, and then divide by 3. So you have 5 plus natural log of 6 divided by 3. And so on a calculator, the way we would enter that is we would put 5 plus natural log of 6 like that, and then we put all of that in parentheses, and then we divide by 3 like that. And so you have 5 plus natural log of 6. I'm going to enter that in there. And then we're going to divide that by 3. And so I get x to be approximately 2.2639. That's my approximate solution there, my decimal solution to 4 decimal places. And this would be, this again would be a little bit harder to check, but you could certainly check this one. And I've been checking them pretty consistently for the most part. So it's never a bad idea to get in the habit of checking these. And for one thing, it gives you some practice on how you enter things on a calculator when you're talking about logarithms and exponential expressions and parentheses and all that stuff. So not bad practice either. So I have 3e to the 3x minus 5. So this would be 3 times 2.2639, like that, minus 5 power. And then minus 50 equals 100. Right? And so you do all the arithmetic on the left side of the equation. So I'd have 3 times 2.2639 power. And so that would give me this. You're not, by the way, when you're checking, you're not adding things to both sides of the equation. You can't do that when you're checking. All you're doing is all the arithmetic on each side of the equation. And so I get 6.7917 minus 5, like that, and then minus 50. And we want to see if this is equal to or close to 100. got to finish the exponent out, so I subtract 5 there, and so I have 25 times e to the 1.7917 power minus 50 equals 100. And now remember, to take e to the 1.7917 power, you need to, and I'm going to kind of put this off to the side here, you have e to the 1.7917 power. Remember, on your calculator, you have to enter e like this. And to do that, you are hitting the second key first, and then the ln key, and that will give you e to that power. So this is good practice with all this stuff here. I think this is actually good to go through all this stuff because it gives you more practice with using your calculator with exponential expressions. And so I get 5.9996 power right there. So I have 25 times 5.9996, like that, minus 50 equals 100. And I think you can see the writing on the wall when you multiply that by 25. So you have 25 times 5.9996, and then you're going to subtract from that 50, right? And I get 99.99 when I do that. And so I get close enough that 99.99 we know is approximately 100. We've been rounding decimals through all this, and so this is definitely going to check. This is our solution down here. Right, so it takes a little bit of work to get to the solution here. There's no question about that. But it is good practice using your calculator, so I do think it's worthwhile to kind of go through that process. All right, so let's finish this. We'll get one more exponential equation done here. So you see lots of different exponential equations. I think that's a good thing to see a bunch of different examples. So you have 3 to the 2x plus 1 is equal to 5 to the x minus 3. And this is going to be kind of a yucky problem at the end, to be honest with you. But we can make it through it with properties of logarithms. Now notice the 3 and this is definitely a type 2 exponential equation because 3 and 5 are not powers of the same number. So there's no way I can use properties of exponents here. I must use properties of logs here. And because I have bases of 3 and 5, it doesn't matter what base logarithm you use. I'm just going to use log base 10. So you have log of 3 to the 2x plus 1 equals log of 5 to the x minus 3. Right? I take the log of both sides of the equation. Then remember, you're taking log of both sides, then you're using power rule for logarithms. So I have 2x plus 1. I bring that down in front, times log of 3. Equals, and then bring the x minus 3 down in front. Make sure you put those in parentheses in both cases, times log of 5. And because I have x's on both sides of this equation, there's really no choice. I'm going to have to use the distributive property in both sides of the equation in order to solve for x. I've got to get rid of those parentheses, and that's really going to be my only way to do that in this problem. So you have 2x log of 3 plus 1 times log of 3. So notice you're multiplying the 2x and the 1, 2x plus 1 by log of 3, right? So you see a log of 3 on both sides of the equation in there, right? I'm definitely using the distributive property to multiply this out. Equals, use the distributive property on the other side of the equation, and you have x log 5 minus 3 log 5. And so notice on that side of the equation, once again there, you're multiplying by log of 5 using the distributive property. So you can see the log of 5 in both of the terms there. All right, so now you have x terms on each side of the equation, right? I have x term there, and I have an x term there. And so you need to get the x terms on the same side of the equation. And what you are doing here is you are just moving terms around is all you're doing. Right, so what I would do is from both sides of the equation, I would go ahead and subtract x log of 5. I'm going to get rid of that term on the right side of the equation and move it over to the left side of the equation. Right, so I subtract x log 5 on both sides of the equation. So you have 2x log of 3 minus x log of 5 on this side, on the left side of the equation. And then on the same step here, we can go ahead and move the log of 3, which is a non-x term, move that to the other side. So I subtract log 3 on this side, and I subtract log 3 on this side of the equation. All right, so if I subtract log of 3 on both sides, on the right side of the equation, I'll have negative 3 log of 5 minus log of 3, like that. All right, this is rather messy here. All right, and then on the left side, since I've got both of the x's on the left side here, I factor out x. Right, because I'm solving for x, I get the x and I just divide it out, or I pull it out as a GCF. So you have x times 2 log 3 minus log 5. Just pull it out as a GCF. Equals negative 3 log 5 minus log 3. And then finally divide by that mess in the parentheses, and you get x equals negative 3 log 5 minus log 3, all divided by 2 log 3 minus log of 5. I didn't put the 5 there. Minus log of 5. Like that. And on WebAssign, they're going to want you to enter it like that. Though the way you enter that on WebAssign, you have to be careful because you're going to have to use all these parentheses in WebAssign also. And so this is the way this thing gets put in, whether it's on WebAssign or on your graphing calculator. You've got to put in parentheses around that entire numerator, and then you've got parentheses around the 5 and the 3, and then you're dividing by, and then parentheses around the entire denominator. And so you have this really ugly expression like this. And so that's the way you're going to enter that. Again, not a bad exercise to put all that in on your paper first with paper and pencil so you can see where all the parentheses go and then enter it on your calculator. I'll certainly let you do that problem. I guess I should enter that on my calculator so that you know what I was getting here. Be careful with, on a graphing calculator, be careful that negative sign that's at the very beginning of some of these terms like that. Remember, you have to use the right negative sign on your calculator also. So this is negative 3 log of 5. Close the parentheses on the log of 5. Then minus log of 3. Close the parentheses on the log of 3. And then close the parentheses on the entire numerator. And then divide that by, put parentheses around the entire denominator. So this takes a lot of patience to enter this kind of problem. There's no question about that. But when I get everything entered in there correctly, I am getting approximately negative 10.0835 power. That's to 4 decimal places, rounding it to 4 decimal places. This one's really not too bad to check, and it's probably worthwhile to check that problem. And so here's, I'm going to go ahead and copy that and paste it to the next page. And let's go ahead and check this. So here's my equation, and we got x equals negative 10.0835 power. Right? That's our approximate solution. So if I'm going to check that, I get 3 to the 2 times negative 10.0835 power plus 1 equals 5 to the negative 10.0835 minus 3, like that. Now on the right side, that's just 5 to the negative 13.0835 power, because I'm subtracting 3 from that negative 10 there. And so when I use the caret symbol on my calculator to raise to that power, this is going to be really small. Wow. I get, so this is, let me go ahead and erase that. So I went ahead and did the calculator, and I got a number that's in scientific notation. I get 7.161862 times 10 to the negative 10th power. So an incredibly small number. And so we're assuming we're going to get the same answer on the other side of the equation, where we're not assuming that. We're hoping that that's what we get. So I have 2 times negative 10.0835 plus 1 on that side of the equation. So I get 3 to the negative 19.167 power, like that, which is also going to be incredibly small. And I get, on this side, I get 7.1617, 1296 times 10 to the negative 10th power. So certainly I get pretty close. These are approximate, not exactly the same value, but that definitely tells me that I've got the right solution here. Those are close enough that that's just rounding error right there. All right, so this finishes our discussion on exponential equations. So textbook homework, if you want more practice with solving exponential equations, which I think would be a good thing to do, we're towards the end of chapter 6 here, remember. And so I'm kind of flipping through my book right now. This is section 6.6 in your book. And the exponential equations that you should look at would be on page 535. And there's both type 1 and type 2 equations here. So the type 1 equations are problems 5, 7, and 9 on that page. There's just a couple at the beginning. And then the type 2 exponential equations would be problems 11 through 25. Odd. So those would be really good practice problems for exponential equations. And so give those all a try. By the way, also, you might look at problems 69 and 71 also for a little bit more practice with using your calculator. 69, 71, and 73. Those would all be good practice also. So those are good practice problems. We're going to look at log equations next time on Wednesday. So have a great week. Please work on your homework. Remember, drop day is today, but I'm hoping that all of you who are watching this video are intending to stay with us in the class. As always, email me. Remember that I have online office hours tonight and tomorrow night and Wednesday night. So don't hesitate to come by and ask questions. So have a great week and do some algebra definitely, and I'll talk to you later.